I'll be taking you to the online textbook here just a little bit. So page, I said 7, I think it's page 8. Yeah. So what is friction? I'm going to go to the online textbook and we'll see what it says. It's OpenStack Physics. I think I told you about this a long time ago, and then since then we haven't really used it much. But on my website today I have a link to section 5.1. And this is about friction, and their definition of friction is a force that opposes relative motion between surfaces in contact. And I guess that's okay, except that, bless you, that to me sounds like maybe a normal force. You know, if you have a couple of blocks here, and they're the surfaces that are in contact, maybe one surface wants to move, like the top surface is wanting to move that way, and the bottom surface is trying to move this way. Is friction going to counteract that? No. So I think it's more about sliding forces, but you can write whatever you want because everybody really knows what friction is anyway. So I'm going to write a force opposing the sliding of two surfaces in contact. I think you could spend a long time trying to come up with a really good definition, and it would be time wasted because we know what it is. All right. Now, number 2 and number 3 we've already been over. I screwed this up in the other class. I think it's because Mr. Pennington used to, but I'm not sure if it's his fault. When there's relative motion between forces or objects in contact, the friction is called blank friction. Kinetic friction. That's not the part I screwed up. The part that I screwed up was the symbol. So what I did is I jumped right to mu, and mu is the symbol for the coefficient of friction. And mu k is the symbol for the coefficient of kinetic friction. But when I write kinetic friction, usually there really is no particular symbol I really care about, as long as you can communicate it. I write F. This is just general, capital F represents a force. And then I'll put a little FR next to it to indicate that it's the force of friction. And then maybe a K after that. It almost looks like a freak force, the way I've written it. But that's my symbol. You're going to see people write this out a bunch of different ways, but that's my notation. When there's no motion between the objects in contact, the friction's called, remember that? Static. Static friction, and that would be force of friction, static. Generally, forces are labeled with a capital F and then some subscript describing whatever it is. The harder two forces are pushed together, the blank the friction becomes. Yeah, greater, stronger, whatever you like. Greater. And I want to go to the equation because I think it's interesting, and I want to see if you can figure out why it is as it is. There's talking about kinetic friction. Oh, first, let's look at this. This is going into a little bit of what causes friction, and this is the part that makes sense to everybody. If you have sandpaper, the sandpaper has bumpy edges, and those bumpy edges might catch or interfere with bumps on something else, so it's harder for them to slide past. But this makes a note that much of friction is actually due to attractive forces between molecules. Every time I highlight it does that. Asks me if I want to take notes or something. Even perfectly smooth surfaces are not friction-free. So can you imagine a really smooth surface that's still grippy? Like a rubber surface, for example. I don't want to let go of this. Oh, what if I go back to there? Hey. Haha. I did it. Okay, so here's the formula for the force of static friction. Instead of a capital F with a little FR and an S, they just call it this. It looks like an F hole on a violin. So the force of static friction is less than or equal to this quantity called the coefficient of static friction times the normal force. And I usually would call this Fn. But this is the peculiar part. So I'm going to write the force of friction static is less than or equal to mu s times the normal force. And what I want to know is why the less than or equal to? Maybe the most interesting thing we'll discuss. Why is it not just equal to? While you think about that, let me show you some muse to amuse you. Well, that's according to this. Could the force of friction be 0? Could be 0. So that's not exactly what this is all about. If you look at this table, we've got static frictions here. Oh no, I highlighted again. Static frictions that are 1, coefficient of kinetic friction is 0.7. 7 or 0.7, 0.5, 0.5, 0.3. Everything in this column is greater than everything in that column. Waxed wood on wet snow. The lowest one on here, as I've told you, is bone lubricated by synovial fluid, 0.016 if we're talking static, and if we're talking kinetic, it's 0.015. So you don't see any zeros here. And by the way, these are the way this works is you take this number and you multiply it by the force between the two surfaces, and that gives you the force of friction opposing motion. All right, Henry Robinson, do you have an answer of why it's greater than or equal to? Or less than? Okay, what's your question? The only way you would ever have to calculate them is in reverse. So let's say maybe I'll give you some concrete and a piece of rubber and tell you to find the force of static friction. And you could put your concrete here, set your rubber on top, and then do what? Try to pull it along with some sort of a scale or a force sensor that'll measure how much force does it take first to begin moving, and then how much force does it take to keep moving. And based on the weight of this, that would give me the normal force. I could calculate it that way. So you can find it empirically. And those numbers in the table are probably not exactly right for the particular examples we have. Okay, so my laptop, I'm using this as an example. What's the, what kind of friction is there between the laptop and the table right now? Right now. Okay, we'll come back to that one. I'm not telling you if you're right or wrong. Actually, yeah. So what is if I wanted to calculate it, let's just say, I'm making up numbers. Let's just say the mu for the table and the laptop being rubbed against one another. Let's say mu static is 0.5. That's kind of middle of the road for coefficients of friction. And let's say that the weight of this, I kind of spoiled it. I should have asked you that. The weight of the laptop is, how many quarter-pounder patties do you think it would be? 8? Is it a couple pounds, you think?
8?
Well, would it be 2 pounds? How heavy do you think the laptops are? 1.5? No. I always think of it in terms of fish. Like, what kind of a bass would this be? If I caught a bass that were this heavy, I'd say it's a pound and a half bass. So that would be 4 to 6. Let's call it 5 newtons. So the weight and therefore the normal force between the table and this is 5 newtons. So if I multiply 5 newtons times 0.5, I get 0.25 newton or 2.5 newtons. That should be that's what I get if I use force of friction equals mu times Fn. But is that actually the force of friction right now? Okay, watch this. Tell me if you see the force of friction changing. I'm pushing a little. Has the force of friction changed? I'm going to stop pushing. Now I'm going to push lightly. Now I'm pushing a little harder. Now I'm pushing a little harder. Now I'm pushing harder. Pushing harder. Pushing harder. There it started to go. I'll do that again. No push. Pushing harder. Pushing harder. Pushing harder. Pushing. And now it starts to move. So in the beginning, before I start to push, what's the force of friction? 0. Why is it 0, Kelton? Because if we were to draw all the forces on this, there's its weight pushing down, there's a normal force pushing up. Are there any other forces? No. Friction is just an opposing force. The moment I do this, though, if I start to push to the left with 0.1 newtons and it doesn't go anywhere, then what's the force of friction? 0.1 to the other way. Now if I push with 0.2 newtons and it doesn't go anywhere, friction is 0.2 newtons. And I keep doing that, and eventually I get up to some force that's as strong as the limit on static friction, and then once I pass that limit, it goes. So that's why this is less than or equal to. And friction's kind of a weird thing. It's almost like it's got a brain. Like right now there's no friction, and it waits for me to try to push, and then it does its thing. And then if I push this way, friction goes the other way. And if I push this way, friction goes back. Yes? Yes. So if I pushed on this with any force less than 2.5 newtons, it wouldn't go. But as soon as I exceed 2.5, it starts to move. If I push with a force of 2.6 newtons, what would the net force be? 0.1, and we could calculate the acceleration using the mass. We could use F equals ma. Well, if I push with 2.5, and then it wouldn't go anywhere. But if I push with 2.6, and then I get it moving, then the coefficient of friction drops from maybe 0.5 to 0.4. So this is the force of friction drops from maybe 2.5 to, I don't know, 2.2. So then it's going to go even faster. But I could just equal that force of friction as I push it. And as long as I push with the same force as the force of kinetic friction, what's going to happen? Yeah, there'll be 0 acceleration. So F equals ma would give you 0. Okay. The equation for the magnitude of kinetic friction looks the same, except there's a little k there, and this mu. By the way, I'll try to write my mu's with really long tails like that. Does anybody know what mu is the metric prefix for? It's for micro. It's 10 to the negative 6th, 1 millionth. Now, what's the operator here for kinetic friction? Do we need this kind of thing? Right. It's once it's moving, and it doesn't really change. So that's just equals. All right. Which coefficient of friction is greater, static or kinetic? You know that one by now. That's static. And I don't want to write down a bunch of examples. Let's just do the highest example. We could talk about them. And the lowest example of kinetic friction, or static friction is the highest and kinetic friction is the lowest. Rubber on dry concrete. We actually did a Google search last class, and we found values from 1 all the way up to 4 for rubber on stuff. And in life, it gets complicated. Does anybody know how dragsters get extra traction at the beginning of a race? They actually put wheels down on the surface, so they spin out. They do the burnout, and that heats up the wheels, starts to melt the outsides of the wheels, and puts a little strip of rubber right on the beginning part of the track. So then they have these sticky wheels that stick to the rubber that they put down. At least that's what I've heard. I'm not a dragster driver or anything. And it's really bad for the environment, I'm sure, but it's really cool, actually. So there's the highest and then the lowest. is bone lubricated by synovial fluid, 0.015. So rubber on dry concrete, and that's mu s equals 1, and bone lubricated. So it'd be two bones with some synovial fluid between. And that's mu k equals, see, it looks like an M. I did it. Mu k equals 0.015. Oh, what are the units for a coefficient? That's a trick question. There are no units for coefficients. Coefficients don't have units. So we'll deal with two coefficients I know of. Well, actually three. We'll have coefficient of friction, coefficient of restitution, and coefficient of drag, or drag coefficient. Number 10, this is just a little example problem. It kind of looks like, if you think, oh, I've got to find acceleration, I've got to write the equation for net force in terms of Newton's second law, and the equation of net force in terms of sum of forces, and do all that stuff, which you could do here, but we don't really need to do that. So I'll draw a picture and then I'll just answer this question. Here's a skier who's sliding along on a horizontal field of snow. It's got a long torso and a couple of ski poles. and there's the horizontal field of snow. And this, like Edward Scissorhands, has anybody seen the artificial intelligence thing? It used to be called DALL-E, now it's Crayon. So I'm on this Reddit. Yeah, so the Edward Churro hands. Yeah, it reminds me of Edward Churro hands. So I'm getting distracted. What we're trying to find, it says skier plus her skis is 62 kilograms. That's the mass. She's experiencing a 30 Newton force of friction. What's the coefficient of friction between the skis and snow? And is this static or kinetic friction? Which part can we just automatically answer right now real fast? Yeah. What kind of friction is it? Kinetic. So the other part, trying to find the coefficient of friction between the skis and snow. So I'm just going to jump to this formula right here. The force of friction, I'm just going to write it. The kinetic friction is equal to mu k, that's what we're trying to find, times the normal force. So if I can find these two things, then I've got it. So let's assume she's going to the right. She's traveling this way. The force of friction is what? 30 newtons. And I don't really like this. I don't know what to do here, but I'm just going to write force of friction is 30 newtons to the left, which numerically in my little equation really should be negative 30. So that's the force of friction. I don't like this negative right now, and I'll tell you why in a second. So mu k, that's what we're looking for. And I need the normal force. What's the normal force? What exerts the normal force? So the weight of the person in the skis pushes down on the earth with the normal force, and then the equal and opposite normal force is the normal force of the earth pushing against the person. So I'll just show them all. So the weight is mg. I calculated this last class, so I'll just cheat. I think it's 607. 62 kilograms times 9.8 running into this, which is 607 newtons. So that means the normal force is 607 newtons. And if the normal force is not 607 newtons, let's say it's 650 newtons, what's going to happen to this person? They're going to start levitating. So it's got to be the same, assuming this person is not going up or going down. So there, we've got the normal force. So I could put 607 newtons in here. And so to find mu k, I just need to do 607 divided by 30, right? Or sorry, 30 divided by 607. I think it's 0.049. It is? Did you already do it? Okay. So mu k. But technically, the way this looks here, if I divide negative 30 by 607, I should get negative 0.049. But we just don't do that. That's mu k. So there's a 30 Newton force of friction, and mu is a positive number. You just never see tables with negative numbers. You just need to know here that this mu multiplied by that normal force, in this case, gives the force opposing motion, so it's to the left, so the force is negative. But the signs don't really work out there. The homework is not that. Homework is to do number 10, 11, and 12. These are all problems involving friction. And probably some kinematics, and maybe some Newton's second law. Probably some of all three of those things.